Good morning, everyone. We'll start with today's class now. Okay, I hope the PPT is visible to all. So in the last class, we were discussing about the reconstruction method. So basically, we were discussing about the stereo vision, right? Or the stereopsis method, where we take two images of a particular scene and we try to do the reconstruction. So we saw that there are three reconstructions possible. So in general, when you're trying to reconstruct an image or reconstruct a 3D scene from two images, we say that it would be the reconstruction would be in the projective space. So when you say it is the projective space or a projective reconstruction, what we mean is that here these the parallelism between the lines or the lengths of the lines, etc., they won't be preserved, right? They won't be preserved, but the only properties that would be preserved is that the lines in these images or the 3D reconstructed and the 3D reconstructed model would remain the same, and also the fact that the two lines which are which are incident on each other or which intersect with each other, those point of intersection also, not exactly the point of intersection, but those two lines also will intersect in the reconstructed image. So those are the only two, only some of the very few properties that are preserved for a projective reconstruction. But when you go with an affine reconstruction, what we see is the parallelism is preserved. That is, if you have in the 3D scene, if you have two lines which are parallel to each other, you see that in the reconstructed image, if it is in the affine space, then those parallel lines would also remain parallel in the reconstructed image. Similarly, if you have these are some of the set of parallel lines that could exist, and all those parallel lines would still remain parallel. However, the length as well as the angle between the different lines would differ, okay, when it is in a affine reconstruction. But if you go to a metric reconstruction, what we see is that the parallel lines remain parallel. At the same time, the length of the parallel lines or length of all the lines would still be preserved, and even the angle between the lines also would be preserved, right? So if you want to make any kind of measurements with respect to the lengths of any objects or the size of an object, or let's say the angle between any two lines or planes, etc., we go about with metric reconstruction, okay? Or we always take the measurements in the metric space because the lengths and angles are preserved only in the metric space. Now, this is a brief summary of what we discussed in the previous class. So if you want to compute a projective reconstruction, the different methods that we use is, so what we do is we try to find out the camera parameters P and P dash. So we have two cameras and each of the camera parameters is given by, or the camera matrices is given by P and P dash, and you have Xi, which are the set of reconstructed points in that particular 3D scene. So the different steps is first to compute the fundamental metrics, given that the cameras that you use are uncalibrated and you do not know the parameters of the camera, the intrinsic parameters of the camera. So in that case, you compute the fundamental metrics and you compute that from the point correspondences. So we assume that from the two images, we find the point correspondences x dash, okay, using some method, probably using some correlation method or some kind of a similarity matching method. You find point correspondences. Once that is known to us, we compute the fundamental metrics, and from the fundamental metrics, the next step is a camera retrieval. So in a camera retrieval, what we do is basically you're trying to compute the matrices P and P dash, and once that is known, we go for a triangulation method, okay? In the sense, if you have, let's say, two image points P and P dash over here, or X and X dash over here, what we do is we try to back project these, okay, according to the pinhole camera projection model, and then this point of intersection would give us the 3D point, right? So these are the different steps which are involved in the projective reconstruction. Now, if we want to, let's say, make some measurements of the reconstructed model, we have to go, or we have to ensure that the reconstruction is in the metric space or the Euclidean space, right? So if we want to go to the metric space or the metric reconstruction, what we need to do is we need to go from the reconstruction or projective space to the Euclidean space, or basically the metric reconstruction, right? So in order to do that, there are two ways by which you can do. You can go by a direct method where you can convert from projective space to the Euclidean space. So that is something which we'll discuss in today's class. Now there is another method where we can go from projective to metric space indirectly, that is through the affine space. That is, first you go from projective to affine space, and then from affine space to the metric space or the Euclidean space, right? And this kind of an approach, this indirect approach, is what we call as a stratified method, and that is what we saw in the previous class. So if you wanted to go from the projective space to the affine space, okay, in the stratified method, what we did was first trying to find out what is the plane at infinity, which is given by pi infinity. So to find pi infinity, what we make use of is, in the affine space, we know that the parallelism between lines are preserved. So we try to find out parallel lines, that is, lines which are parallel in the actual 3D scene. We identify those lines on the reconstructed image, and we try to find out the points at infinity. So once we know the points at infinity, from there you can find out what is the plane at infinity. So provided that those points at infinity are not collinear, you can find out what is the plane at infinity, right? So once you find out the plane at infinity, which is given by pi infinity, from there you can find out what is the transformation matrix that needs to be used, or what is the mapping basically from the projective transformation, or from the projective space to the affine space. So once you have calculated h, that is the transformation matrix from pi infinity, using this equation, on applying h to all the points in the reconstructed image in the projective space, what we get would be the corresponding points in the affine space. Okay, so therefore we move from the projective space to the affine space. Now from affine space, next we need to go to the metric, the Euclidean space, or the metric reconstruction, right? So to go to the metric reconstruction, what you do is you need to compute the image of absolute conic, which is abbreviated as IAC, okay, or which is also denoted by the notation omega, right? So in order to compute the image of the absolute conic, which is given by omega, what you do is, there are different methods by which you can do it. One of the method is that if you know the intrinsic parameters of the camera, if you know the intrinsic parameter k of the camera, then from there you can compute the IAC. How you can compute is, you can take omega is equal to k transpose, the whole inverse. From there you can calculate omega. Now once you know that, and the M, which are basically the camera matrices, you can calculate what is A, and from A you can calculate what is H, right? So H is basically the transformation matrix which transforms, or which maps the affine space to the metric space. So once H is computed, you can apply H to all the points in the reconstructed image in the affine space, to then convert that to the metric space. Okay, so this is the stratified approach. Now in today's class, what we'll be discussing will be the direct method. So in the direct method, in the sense, you are trying to, from the projective space, the reconstructed image from the projective space, you can directly convert that, or you can rectify is the name that we use, you can rectify that to the Euclidean space, okay, or from the projective reconstruction we can directly rectify that to metric reconstruction, okay. And in order to do that, what we do use is, we use the IAC, the information of IAC, or basically the image of absolute conic, which is given by omega. This information can be used in order to do a direct reconstruction, okay. Now, this direct reconstruction, we can obtain it or we can achieve it again in two different ways. Okay, so in the first approach, what we do is, let's say you know the internal camera parameter, which is given by K. Okay, so if you know the or if you know omega, you can calculate the internal parameter of the camera, right? So internal parameter of the camera means it is inclusive of, you know, the length and angle measurements. So basically intrinsic parameter of the camera means that it includes the pixel dimensions, it includes what is the skew or the angle between the two different image axes, the magnification factors, and so on. That means the intrinsic parameters of the camera are basically measurements of lengths and angles, right? So if this internal parameter can be obtained from the image of the absolute conic, then what you can say is, you can say that right now you're no longer in the projective space, but you are in the metric space. And why you say you're there in the metric space is because you can make use of the information of the lengths and the angles which are present in the internal camera parameters or the intrinsic parameters of the camera. Okay, so one approach is using the information of the IAC or omega, you can find out the internal intrinsic parameters, and therefore from those lengths and angles you can convert from the projective space to the metric space or metric reconstruction. That would be one method. Another approach that you can use is, you can make use of something what you call as the ground control points. Okay, so what ground control points mean is, those are points which are in the actual 3D, whose, or let's say whose actual 3D coordinates are locations or points are known to us. Okay, like for example, let's say we are taking in this particular scene that we have. Okay, let's say we assume certain points. Okay, some, usually we take the corners because that is easier for us to locate and find the correspondences of. So let's say we locate some corners. Okay, it could be corners of the house, corners of the windows, okay, and some points. So we identify certain points, okay, which can be called as the ground control points, and we assume that for these ground control points, okay, we know what are the actual 3D coordinate values. Okay, so once you know those values, what happens is, now basically what you're doing is a reconstruction, right? So let's say you have reconstructed. Okay, so this is the projective reconstruction, the points which have been obtained in the projective space or the projective reconstruction. So for those points, if you know what are the actual values in the world coordinate for those exact points or the ground control points, that means I can try to find out what is the mapping between these two, right? So since I can find out what is the mapping between these two, that would be another, I can just apply this transformation matrix to all the points in the image to convert that to the Euclidean space. Okay, so this is the second method. Okay, and which is called as the as using ground control points. So the same thing has been mentioned here in this equation, that is the ground control points can be represented by the notation over here, which is given by capital X E I. Okay, so basically that means these are in, this is in the Euclidean space, right? So xei, which is equal to h, which is the mapping between the 2 points, and xi is the points, reconstructed points in the projective space, right? So if you know this xi, if you know this xi, in the sense what you're trying to do is you're trying to convert from the projective space to the Euclidean space or the metric reconstruction, right? So if you know, or once you have these points in the projective space, right, and you use these control points whose Euclidean coordinates are known to us, then what I can do is I can find out h from this equation. So if I find h, then I can just apply that mapping on all the points in the projective space in order to convert that into the Euclidean space or the metric reconstruction, right? So this is another method by which you can directly convert from the projective reconstruction or rectify from the projective reconstruction to the metric reconstruction. And here there are some constraints over here, okay, that is we need to have at least 5 points in order to have a faithful reconstruction, and also that these points should not be coplanar, okay. So you need to have at least 5 points, and which at least four of which are not coplanar, in order to ensure that there is the metrics that we find h, okay, should give us a faithful mapping between the Euclidean space and the projective space. Okay, so I'll just try to summarize what we have been discussing so far. Okay, so what we discussed earlier is that we can have when we do measurements of lengths and angles, we have to do that in the metric space, right? But a projective reconstruction is usually easier, okay, because it just involves finding the fundamental metrics from the image correspondence pairs, and then you using the pinhole camera projection model, you just try to back project it and then find out what is the point of intersection, which gives us the 3D point, right? So it is as simple as that, okay, because it does not involve any kind of constraints with regard to the parallelism or the lengths and angles, etc. So if you want to include all this, then there would be more parameters or more information that has to be incorporated, and therefore the reconstructions becomes more difficult, right? So the easiest way of reconstructing a 3D reconstruction from given two images would be a projective reconstruction. Once you have a projective reconstruction, if you want to, let's say, take some measurements from the reconstructed scene, you cannot do it in the projective space. It has to be done in the Euclidean space, right? Because the lengths and angles are preserved only in the Euclidean space. So therefore you will have to convert from the projective space to the Euclidean space, or you can say from a projective reconstruction you need to rectify that to the metric reconstruction. And in order to do that, you have two different ways. One is the stratified approach, where you first convert from the projective space to the affine space, and then from the affine space to the Euclidean space. That is one method. Another method, the second method, is a direct reconstruction, which means or a direct transformation, where you directly transform the projective reconstruction to a metric space or a metric reconstruction. So in order to do that, that is directly from the projective space to the metric space, you can use two different approaches. One approach would be to make use of the IAC, or the image of the absolute conic, from which you can find out the intrinsic parameters of the camera. Since the intrinsic parameters of the camera involves measurements of lengths and angles, then you can say that you are no longer in the projective space but in the metric space. The second method is where you can make use of ground control points. That means you identify points within an image whose actual coordinates are known to us, okay, and from those coordinates, so you know what are the actual coordinates, and you have those reconstructed coordinates from the projective space, right? So what you do is, because you know what are the actual coordinates in the Euclidean space and you have the reconstructed points from the projective space, you can find out what is the mapping, right? So this mapping you are finding out with respect to only the ground control points. So, and once this mapping is obtained, you apply this mapping to all the points in the reconstructed projective space in order to reconstruct back, or in order to rectify that and bring it to the metric space or transform it to the metric space. So the choice of the ground control points is very important in order to ensure that the transformation matrix H is a faithful transformation, or it is the correct mapping. So you need to have at least 5 ground control points, and which are not coplanar, in order to ensure that the mapping is good enough. Okay. You can have more number of points. The more the number of points, the better would be the kind of mapping that you can obtain. Okay, so that is with the direct reconstruction. Now this projective reconstruction or the direct reconstruction, what we were speaking about all this while, was for the stereo vision, where you're saying that given two images, you're trying to reconstruct the image, and for that you're trying to compute the camera parameters, right? And from the camera parameters, or assuming that the camera parameters are known to us, if it is not known, what we do is we kind of calculate the camera parameters itself from the image correspondence point pairs, and then from that information we are trying to reconstruct the image. Okay, and we are doing it with only 2 points. Now, next kind of method which comes under the 3D reconstruction is the structure from motion method. So in structure from motion, how it is different from stereo vision is that in structure from motion, you use multiple images. That means you need to have more than 2 images. Okay, and in structure from motion, the knowledge of the intrinsic parameters is not necessary. Okay, so even if we do not know the camera calibration matrices or the intrinsic parameters of the camera, we can still reconstruct the image from the information that we obtain from the multiple images. Okay, and here this is an illustration of this structure from motion problem. So here if we say, we can assume that here we have one camera, okay, and this is the image, let's say I1, which has been obtained from the first camera, and let's say the matrix of the first camera is given by M1. Similarly, you have the second camera, the image I2, which is formed from the second camera, okay, and the second camera matrix is given by M2, okay, and then you have the image I3, okay, which is formed from the third camera and the corresponding matrix. Okay, so third, or let's say you have multiple over here, and this is the mth camera. Okay, if there are m cameras, and this is the that is the camera matrix corresponding to the mth camera. Okay, so you can have multiple cameras, which is basically taking the image from different viewpoints. Okay, and it is taking the image of the same 3D scene. Okay, now once you have these images, what we do is, just like how we do for the previous stereo vision, we need to have point correspondences, right? That means I need to identify points, okay, which corresponds to the same point in all the images. Like for example, I might have what I say, a point here which corresponds to, so you have this here, let's say you have the point x2j, so x1j, let's say that is 1j, where j is equal to 1. Let's say x11 is a point, is this particular point which is present in image 1, okay, and this is the first point in image 1, right, which is basically the image of this point over here, which is given by, let's say, capital X1. Similarly, you have in the second image, you have another a point over here, okay, which is the image of this particular point itself, right? And let's say this point over here is basically given by x21, right? Because it is the image of this capital X1. And let's say here you have another point xm j, in this case it is xm1, okay, which is again the image of this same point here, right? So what I'm trying to say is that given these multiple images, what we try to do is we try to find out which are the correspondence. So here we cannot no longer say correspondence point pairs, because it is not pairs right now. You'll have a set of points which are correspondent to each other, in the sense those 3 points all represent the same 3D point, right? So you can have, let's say in this particular image, you can have multiple such, image points whose correspondences we have found out, and each of these points refer to multiple 3D points, right? So I can have x1j points, correspondence points over here, right? Where j can be any value from, let's say, 1 to n. Okay, so let's say we are considering, or we are trying to reconstruct n 3D points. If there are n 3D points, then that means the value of j would range from 1 to n. Okay, so accordingly you will be having, in for all the images, you will be having that many, that is n 3D images of those n 3D points would be present. So therefore the notation x1j, x2j, xmj, right? And here m stands for how many number of cameras you have, or how many images you are having over here. So depending upon how many cameras you are taking, or how many viewpoints you are having, right, accordingly you'll be having that many number of projection matrices also, right? Projection matrices or the camera matrices. So let's assume that that number is m, small m, right? So that means you have small m number of cameras, or small m number of viewpoints. Okay, so in general we can say we'll be having mn correspondences, which is given by small xij, right? And from there there'll be m projection matrices and n 3D points, right? Now, why we say it's a structure from motion is, here these projection matrices, which is given by mi, we can assume that, okay, I have a camera over here, I took an image from a scene, and provided that scene has not changed its position, or it is not a moving scene, I can assume that it is equivalent to moving this camera to this position and taking the next view, or moving this camera to this position and taking the next view, and so on. Okay, so it is equivalent to saying that if you're taking different cameras and taking the image of this 3D scene from different viewpoints, it is also equivalent to saying that you are kind of changing the position of the camera simultaneously, and taking the images from different viewpoints, right? So hence therefore you can call it as motion, because the camera is basically moving over there. And here we say structure because we are trying to reconstruct the 3D points xj, right? And these are the different 3D points that we are trying to reconstruct, right? So from on reconstruction of these different 3D points, what we are trying to do is we are trying to reconstruct the whole image, right? So, or basically we are trying to find out what is the structure of the whole image, right? So therefore you say that it is a structure. So basically you're trying to determine the structure of the 3D scene from motion in the sense motion of the cameras, or by trying to capture the image from the different viewpoints. Okay, so as I said in the earlier, just before, in the case of stereopsis, what we assume is that the camera calibrations is known to us. So it is a calibrated camera. The intrinsic parameters are known to us. Okay, and the extrinsic parameters are basically determined. Okay, with either with some extra information other than from the image correspondence pairs, you can determine that, right? And but basically it is calibrated, or we assume that the intrinsic parameters are known to us, and from that information we try to reconstruct, and basically you have two images for that, right? Now there are possibilities where the intrinsic parameters may not be known to us, okay, or that it may change over time also. So in such cases you can make use of the structure from motion reconstruction method. But in the case of structure from motion method, you need to have multiple image views or multiple images in order to because we do not know the intrinsic parameters, you need to have multiple images in order to do a good reconstruction. Okay, so basically this is called as the SFM problem. Okay, for structure from motion, short form is SFM. And what you're doing is you have the match points or the correspondence points as discussed earlier, right? There will be mn correspondences, and from there what we do is we're trying to reconstruct the structure, in the sense we're trying to find out the n 3D points, capital X, okay, capital Xj. We are trying to determine that, okay, from apparent motion of the cameras, okay, in the sense given capital Mi, which basically represents the different matrices of the camera. Okay, so here we assume that there are m cameras, and here we assume that we are trying to reconstruct n points, right? Okay, so let's say this is the kind of image or the 3D scene that we are you are looking to reconstruct. In that case, let's say the different viewpoints that we may be considering for the reconstruction may be these. Okay, just an example. So from these viewpoints, as you see here, if you can observe, there are some points which have been plotted over here, right? Some points which have been identified. So these points are the correspondence points which are used for, so corresponding to this point, I have this point here, as well as this point here, right? Now corresponding to this point over here, I also have a point here, I have a point here, and I have a point here. So therefore, you try to find out the point correspondences. In the previous case, you just have point correspondence pairs. That means you just had two images. Here you have multiple images. So since you have multiple images, you'll be having, or you need to find the correspondences for all those image viewpoints, right? So once you know the correspondences, then from there you try to continue with the SFM, or the structure from motion method. Now in the structure from motion problem, there could be three instances or three cases that we'll be looking at. One case is where, let's say, we do know the internal calibration of the camera, or the intrinsic parameters are known to us. If it is known to us, then we can work with the normalized image coordinates. Okay, so that is one case. Another case is when it is uncalibrated but a weak perspective, and third case is uncalibrated but a perspective, in the sense it is a strong perspective camera. Okay, so in the first case, where you say that the internal calibrations are known to us and you're working with normalized image coordinates, the kind of reconstruction that you get is the Euclidean reconstruction. Okay, this would be a Euclidean reconstruction. In the second case, where you have a completely uncalibrated, that means the intrinsic parameters are not known to us, but it's a weak perspective. The kind of reconstruction that we attain here is the affine reconstruction. And in the third case, where you have a completely uncalibrated perspective cameras, the kind of reconstruction we have is the projective reconstruction. Okay, so we will be looking at each of these cases one by one. So before that, there are some mathematical concepts and a bit of a recap that needs to be done from some of the previous topics that we have discussed. So here we'll just quickly go through how singular value decomposition can be used. So let's say you're given a square matrix which is given by A. Okay, so for the square matrix given by A, when you're applying a singular value decomposition, it is basically what you're doing is you're trying to factorize the matrix A by writing it as U D V transpose, where U and V are basically orthogonal matrices and D is a diagonal matrix. Okay, so by being able to factorize A as U D V transpose, what happens is we can the calculations, or when we are trying to, let's say, find out a minimization problem, or when you're trying to use a least square estimation problem, etc., the calculations become easier, right? So singular value decomposition is basically trying to factorize A in such a form, okay, that is a product of the orthogonal matrices along with the diagonal matrix. Okay, and How we use that is, if we are using it for a least square estimation problem, let's say which is given by ax is equal to b, then what you do is you try to factorize a, and then you find out a matrix or a vector which is given by b dash, okay, where it is equal to u transpose u given by this orthogonal matrix, and b is given by this constants over here, right? And from b dash and di, which is basically the elements of the diagonal matrix, you can find out the elements yi, from which again by multiplying y with the third orthogonal matrix vy, you can find out the solution x. Okay, so need not go into detail into this, just understand that by factorizing the vector or the matrix a, you will be able to do the least square solution in an easier way, right? And SVD can also be used when we are using a least square minimization problem. Okay, so let's say you want to minimize ax, given the constraint that modulus x is equal to 1. If you want to minimize ax, then you can, the solution would be just taking the last column of v, where you have a v obtained from the singular value decomposition of a. So we'll be seeing these details later. Now, a small recap on what we have discussed in earlier classes regarding the projection matrices and the pinhole camera concepts. Okay. So till now what we were discussing was we used small x and capital X. Small x to represents the image point, okay, in the image coordinate, okay, and the 3D point, corresponding 3D point was represented by capital X. Now for the next few slides, how we'll be changing the notation would be, we'll use capital P to represent the point on the 3D space, and we can use small p to represent the image of that particular point. Okay, and capital XYZ can be used to represent the coordinate of the 3D point, and small xy can be represented to represent the coordinate of the image point, right? And I can write this small x is equal to dx by z, where d is this distance over here, right? Distance from the center of the camera to the image plane, right? So I can write it as d into x by z, and y is equal to d into y by z. Now, if we are working with the normalized image plane, so when I say normalized image plane, what it means is that we are assuming that there's an image plane which is at a unit distance from the center of the camera. So if it is at a unit distance from the center of the camera, what happens is the value of d becomes equal to 1. So if you are taking the value of d is equal to 1, then what happens is this equation, where earlier it was x is equal to dx by z, right, that becomes x hat is equal to x by z. That means I'm taking d is equal to 1. On taking d is equal to 1, it becomes a normalized coordinate, so x hat is used to represent that it's a normalized coordinate, right? So now I can write x hat is equal to x by z, y hat is equal to y by z, which represents the normalized image coordinates. And the corresponding point over here becomes p cap, okay? P cap represents the image point on the normalized image frame is equal to 1 by z id, which is the identity matrix, 0, and p is a 3D point, right? So this is in earlier cases what we saw was we used to write x is equal to capital Px, where this x was the image point and capital X was a 3D point, and this p was the projection model of the camera. So instead here we are just changing the notations, where this p is equivalent to this small x here, this capital P is equivalent to this capital X here, and this 1 by z id 0 basically represents the camera parameters in this case, right? And this is a case of a normalized image plane. So what happens is when you're working with normalized image planes, the coordinates becomes simplified, and even the camera projection model or the camera projection matrices also gets simplified when you're working with normalized image plane. But you can work with the normalized image plane only if we know what are the internal parameters of the camera. So this one is important when we are dealing with the first case. The first case where you know that there is an internally calibrated camera and you are trying to do a reconstruction, SFM reconstruction from the internal calibrated camera model. Okay, now one more thing you need to remember is that when you are talking about pixels, okay, the pixels may not be always square. It could be rectangular. In the sense, these pixels may have a different dimension along the x direction and a different dimension along the y direction, right? So it may not be a square pixel always. So you can say that or you can add two different parameters k and l, which represents, k represents what is the number of pixels per unit distance in the image coordinate, l represents what is the number of pixels per unit distance in the image coordinate in the y direction. So if we have such two parameters that represents how much is the distance, then I can write x is equal to kf x by z. So here remember that I'm not talking about the this one normalized case. This is the unnormalized coordinate here. So I can write it as x is equal to kf, f is equivalent to the d. Okay, instead of d I can also write f, and k is how much is the number of pixels which are present, right, into x by z. And if it is in the we know that x by z is it is equal to x hat or x cap, right? So I can also write it as kf x cap. Similarly, I can write y is equal to l y cap, right? So I can see, since k is what is the number of pixels which are present per unit distance, okay, in along the x direction, and L is the number of pixels per unit distance along the y direction, I can say the pixel dimension can be given by 1 by k into 1 by L. Okay, and from this values of k and l, I can determine what is the magnification factors which are given by alpha and beta, right? So alpha can be written as kf and beta is equal to lf, and these are expressed in pixel units. So here this alpha and beta, okay, these magnification factors are one set of intrinsic parameters of the camera. So what we are discussing here is we are trying to find out what are the intrinsic parameters of the camera. So when you say internal parameters of the camera, what all does it signify, right? So one set of intrinsic parameters is alpha and beta, which is basically determining what is the pixel dimensions. It is a function of the pixel dimensions, right? Now, we also know that when we are taking an image, when you are considering an image, okay, usually the image center by default, when we are considering an image, the image center is or the image origin is considered to be at the top left corner, right? But when you're working with images, the image center has to be over this point, right, aligned with the camera center, right? So in order to transform or translate this origin to the center of the image, you need to do a translation with respect to x naught is the offset that you give along the x direction, y naught is the offset that you give along the y direction. So I can write x and y in this form, where x is equal to alpha x hat plus x naught and y is equal to beta y hat plus y naught. So here this x naught and y naught, which are basically the offsets that you give in order to change the origin to the move the origin to the center, then these two are again the another set of intrinsic parameters of the camera model. And another parameter, intrinsic parameter you have is theta. So basically what that means is we are assuming that the image axis are it is perpendicular to each other, okay, but it may not be always perpendicular to each other, right? So there might be a small skew. So this angle theta represents what is the skew, okay, or the angle between the two image axis, right? So incorporating all those different parameters together, you can write the internal calibration matrix as shown over here. Okay, you can calculate the internal calibration matrix using this formula where I write k is equal to, okay, these are the elements. So what are the different parameters you have is alpha and beta, which are the magnification factors which are dependent on the pixel dimensions. Then you have x naught and y naught, which are basically the offsets used to move the origin to the center, and you have theta, which is basically the skew between the image axis. And all these together are the parameters that determine what is the internal calibration matrix. So you have these five parameters. And one more point you need to remember is that we have already seen earlier that p hat is equal to 1 by z id 0p, right? And that is for an normalized image coordinate, right? So you can, if you're going to a unnormalized case or a general case, I can write p is equal to kp hat, right, where k is the internal parameter of the camera. So on substituting, I can write it as p is equal to 1 by z k id 0p, right? Or I can, this particular equation over here, k id 0 can be represented by capital M. So I can also write it as 1 by z mp. Okay, so I can write small p is equal to 1 by z mp if it is a general case. This is the case of a normalized image coordinate. In the general image coordinate, I can write it as 1 by z mp. Okay, so those were the intrinsic parameters. Now, when we say extrinsic parameters of the camera, it is nothing but rotation and translation. Okay, so that means what you're saying is basically the camera, when you're trying to move the position of the camera, the transformations that are involved is a translation and rotation, right? So this translation and rotation basically forms the extrinsic parameters of the camera. And when you're denoting that in the general form, okay, so here this matrix M, it would involve R and T. So here this one, this K over here represents the internal parameters, and here this rotation and translation together, this one what represents the extrinsic parameters of the camera. And therefore when I say camera projection matrix, that would involve both the internal parameters as well as the external parameters. Okay, and the size of this capital M over here would be 3 cross 4. In the sense, since you have a rotation matrix with 3 independent parameters, you'll have it as 3 cross 4. Okay, 4 because here it is basically in the homogeneous form for a 3D coordinate, right? Okay, so I guess we can stop over here. So what we were discussing so far. Okay, let me just quickly. Okay, we have 5 more minutes, so I think I'll just continue here with the internally calibrated perspective camera. So what we saw so far was what are the different intrinsic parameters and what are the extrinsic parameters of the camera, right? And we have come across all these equations where we write P is equal to Kp hat, okay, where P is given by xy1, which is a homogeneous form over here, and K basically represents the internal camera parameters, right, or the internal calibration matrix of the camera, which is given by this form. Now we discussed that there are 3 different cases, right? The first case is the internally calibrated perspective cameras, and we saw that it is basically a Euclidean reconstruction which is obtained, right? Now here, since it is internally calibrated, what that means is that the intrinsic parameters are known to us. Okay, so since the intrinsic parameters are known to us, we work with the normalized image coordinates, right? And what you do is, so if since we are working with normalized image coordinates, our general expression Pij would be equal to P hat Ij. Okay, P is going to be equal to P hat because we are going to work with only the normalized image coordinates. So wherever we are representing the notation P, that represents P hat, because this is an internally calibrated camera. And as discussed earlier, we can represent it this way, where I have Pij is equal to 1 by Zij Ri Ti 1. Okay, so here Ri and Ti are basically the rotation and translation matrices, right? And P is the image point, and capital P is the world coordinate. Now here what we see is one of the important properties over here is that in an internally calibrated perspective camera, if we are doing a rotation and translation over here, right? What happens is that the image point, okay, so would still remain the same. That is, it is equivalent to one of the concepts that we saw in the previous class. That means, let's say I'm doing a reconstruction, okay, and I get a particular, point over here, PJ, and let's say I'm again doing a reconstruction, right, with the same image, image points over here, set of image points. I get another reconstruction, let's say PJ dash. In that case, this PJ and PJ dash, they are related with each other, or they can be mapped with each other, okay, in the Euclidean, by a Euclidean transformation. That means if I apply a rotation and translation to this particular reconstructed point, set of points, I get this P dash J, okay. But all the while, the images or image points that we have, the correspondence points, remains the same, Pij. So what that means is, here applying a rotation and translation, or by varying this rotation and translation over here, okay, it is invariant for the image points, or the image points over here will not change, or what you're saying is that it will not have an effect on the external parameters, or when you're trying to apply the rotation and translation, it will not have an effect on the image, okay. So that is the same as that of the concept that we discussed in the previous class. The same applies for the SFM, or the structure from motion reconstruction also. So that is basically what you call as the natural ambiguity of the problem, okay. Okay, I think we'll just stop over here, because we do have some more explanations over here. Okay, so next class we'll continue with the internally calibrated perspective camera. So today we won't be having a quiz. Today's quiz we'll just postpone it to the next class. Okay, so in the next class on Tuesday, you'll be having 4 questions for the quiz. So 2 questions would be on the topics that were discussed today, and 2 questions you'll be having from the topic that would be discussed in the next class. That is on Tuesday's class. Okay, if you have any doubts, you can ask me now.